All right, Sebastian is continuing with his third talk on constant mean curvature surfaces. Go ahead.
So thanks. In the last two talks, we learned how to describe constant mean curvature surfaces and particularly minimal surfaces in the free sphere in terms of families of flat connections. So let me just recall what we have seen. So we have this so-called associated family of flat connection, which is basically the Levi-Civita connection or induced connection on a rank 2 complex vector bundle, and then we add the complex linear part of the differential of the minimal surface with some scaling factor, and we subtract the complex antilinear part. And this is a family of flat connections with the following properties, namely, what we know is nabla lambda is unitary for the standard Hermitian metric on our rank 2 bundle for all lambda in the unit circle. So this can be seen as the intrinsic closing condition, or that we really have a solution of the Gauss-Codazzi equation. And we have some other properties, namely the second important thing is if we look at the 0-1 part of these connections, then this extends holomorphically to lambda is 0. So this is just given by this del bar of nabla plus or better minus lambda phi star, and this just extends nicely to lambda 0 in a very holomorphic way. But if we do the same thing for the 1-0 part, we get this is del nabla plus lambda inverse phi, and this gets a first order pole with residue. This is something which is usually called a Higgs field phi, and this phi is nilpotent. This is the condition that our map will be conformal in the end. And we can also read off whether the map is an immersion or whether it has branch points. So if phi is nowhere vanishing, we get an immersion, for example. And the third condition is that there exist 2 points on the unit circle as 1. So for minimal, this would be 1 and minus 1, such that nabla lambda I, for I is 1 or 2, is trivial, so has trivial monodromy. And in that case, we can recover a minimal surface or a CMC immersion as we gauge between these two connections, nabla lambda 2 times f. And then f is minimal or a CMC immersion, depending on whether lambda 1, lambda 2 are plus minus 1, or what we angle between these 2 points is. So this is some computation I do not want to show you today, but I want to discuss how to construct such kinds of families of flat connections. So we have a bunch of properties, and we need to satisfy all these 3 properties in order to obtain a harmonic map or a minimal surface or a CMC surface, which is well defined. And there was the observation by Hitchin, I discussed that shortly yesterday, that in the case of torides, or in the case of Riemann surfaces of genus 1, it is good enough to not specify the actual family of flat connections, but only certain invariants of this family of flat connections, like the gauge classes depending on the spectral parameter lambda. So this is this basically reduces it to some much more finite dimensional or classical problem of specifying monodromies or traces of monodromies, if you like, in terms of holomorphic, and then in the end it turns out algebraic geometric data. And we want to do the same thing. And it turns out that there is a nice story which is originally due to Delin, and it connects with other work by Hitchin, namely so-called Hitchin self-duality equations, where he introduced a nice notion where we really can study such kinds of family of flat connections in a very nice and good way from a complex geometric point of view. So these families of flat connections basically give us holomorphic curves of genus 0 in a certain complex space. And idea is to specify nabla lambda by its projection to the moduli space by factoring out the gauge group transformations of flat connections, the theorem moduli space. And the problem with this is that let me go back, that we get certain kinds of singularities. So even if the lambda, the 0, 1 part extends nicely to lambda 0, the 1, 0 part gets a first order singularity. So if we just go to the moduli space, it means that we have a very complicated, or at least, it's hard to understand exactly what the monodromy does. It certainly blows up, and there are some kind of asymptotic formulas for what happens with that monodromy, but it's not easy to capture this first order pole property in terms of just the monodromy or something like that. So what we should discuss is a certain kind of compactification of this moduli space, this theorem moduli space, is such that we get not only maps from C star, from the complex plane without 0, but such that we get really projective lines inside our new moduli space. And this can be done by the so-called Delin Hitchin moduli space. So this was an attempt of Delin to describe the hyperkähler twistor space of the Hitchin moduli space of solutions of the self-duality equations in terms of complex geometric data. And this is exactly what we need to study such kind of curves. So let me try to explain what we are doing here. So we restrict to the case of Riemann surface. And then we have the following definition of Delin, and I just stated here once, but usually I will drop that. An integrable or flat lambda connection on a complex vector bundle, and our situation, it will always be the trivial vector bundle V over Riemann surface is a certain triple lambda. So lambda is a complex number, del bar is a holomorphic structure, and D is a certain differential operator. So lambda is in a complex number, del bar is a holomorphic structure. So it gives us the structure of a complex vector bundle of a holomorphic vector bundle V over the Riemann surface. And D is an operator, first order differential operator, which maps sections in V to 1-0 forms, or likewise sections in K tensor V, such that we have the somehow del Leibniz rule, which is rescaled by this element lambda. So we had the Leibniz rule for the del bar operator. Now we have imposed the following Leibniz rule: df, I take a function and I multiply it with a section, should be, I scale the 1-0 part of the differential by my complex number lambda, and then I tensor it with S plus just f ds. So it rescales the somehow the symbol, and then I also need to specify what integrability or flatness means. So it basically means that if we take the natural induced operators on the bundle of the 1 forms and 2 forms, then we get the corresponding flatness condition del bar D plus D del bar is 0. So this is somehow flatness, and I will describe that in a second what it really means computationally. So this is the definition due to the Delin, and it's basically, it's very simple. So D is just the somehow the 1-0 part of a connection if lambda is 1, and otherwise it's a rescaled version of that. And here we also have this flatness condition. But let me give you some examples to make clear what happens. So if lambda is 0, then what we get is that D is actually tensorial. So let me go back here. So we see from the condition, from this condition here, that if lambda is 0, we just get a tensor field. So it's a element then in the space. It's an element in the space K tensor the endomorphisms. And if I impose certain SL2C conditions, then it's a section in the trace-free endomorphisms. So, but this only holds for lambda 0 because we have a tensorial object. And then flatness, namely this D del bar plus del bar D, just means that this field phi is holomorphic. So we have a holomorphic section in this bundle K times the trace-free endomorphisms of our bundle. And this del bar and such kind of phi is usually called Higgs pair in the Higgs bundle community. So this is the special case lambda is 0. Now let's look at another special case, namely lambda is 1. Then we can consider del bar plus D. And if we look at the Leibniz rule for both elements, namely for the del bar and for D, we see that this guy is a classical complex connection. It's just a connection. And flatness of lambda del bar, lambda is 1, del bar D means that the connection del bar plus D is flat. And finally, if lambda is not equal to 0, we can rescale the D part, and then we get del bar plus 1 over lambda D is a flat connection. So basically it's just it's a very simple basic idea to decompose the flat connection into 0-1 part which gives us a holomorphic structure as we learned yesterday, and into 1,0 part, which which can be rescaled. And if we do that, then we get the space of lambda or integrable lambda connections. And this is somehow, it looks like a very innocent definition, but it turns out to be quite useful and intriguing. So what we have again is the complex gauge group of maps G into from sigma into SL to C in our situation, and then we can construct the so-called Hodge modelized space of our Riemann surface sigma to be the space of lambda connections on our bundle V modulo gauge transformations. And as yesterday, we should restrict to irreducible lambda connections. So it means there's nothing invariant, no invariant line subbundle, or so-called stable lambda connections. So stability for lambda connection when lambda is 0, so for a Higgs pair, is some kind of a generalization of a stability for the holomorphic vector bundle, and it again corresponds to irreducibility of the corresponding connection. So we restrict to semi-stable or irreducible lambda connections. The irreducible or stable points are again the smooth points of this complex space. So this space is a complex analytic space again. And what we automatically get by construction is that, because maybe I should write this out. The gauge transformation. So if you have a gauge transformation and a lambda connection consisting of this triple, the gauge transformation just acts by in the standard way. So we gauge the holomorphic structure, and we just gauge the operator D. So this just means that we decompose it with as a map with the anamorphism, and then we apply G inverse, and the same for D. So if, for example, if lambda would be 0, D is just a tensor field or a Higgs field, and then the gauge action is of course just conjugation. And in the case lambda is 1, we just have ordinary gauge action on the flat connection. So this gauge group acts on the space of flat lambda connection, and we have this modelized space, and this modelized space is admits a natural map to C, to the complex numbers, by just mapping the gauge class to the point lambda in the complex plane. And then of course one can compute that the dimension of this space is 6G minus 5, so 6G minus 6 plus 1 for SL to C. And G is, maybe I should denote it by gamma here. Gamma is the genus of sigma. Okay, so we have a deformation of our theorem modelized space. And maybe you already observed that if we have a family of flat connection, we get a holomorphic curve into this space just by, or basically a section. So if for our nabla lambda, what we can do is we obtain a section of this projection here. So a map from C into this Hodge moduli space, which projects down to the identity. For nabla lambda, as before, the associated family, we obtain a section of our projection pi. Namely, what we do is we take lambda in C and map it to the gauge class of lambda when we take del bar nabla minus lambda phi star. And then we rescale with lambda the 1,0 part. So we add here phi and then plus lambda del nabla. So, and the property that we have a family, the associated family of flat connections, so the flatness just implies that we really map to flat lambda connections. So this property is satisfied. And the first order pole property exactly means that this map into the Hodge moduli space is holomorphic and extends holomorphically to lambda 0. So this extends nicely to lambda 0. And we should do the same for infinity and also introduce a certain real structure on the moduli space in order to really be able to state a construction theorem for harmonic maps. So how does this work? We use the so-called Delin gluing. So if we have a Riemann surface, there's naturally the complex conjugate Riemann surface sigma bar. So complex conjugate Riemann surface. So for example, if you define the Riemann surface by this endomorphism J, you will use minus the rotation by 90 degrees. You will use minus J as your new complex structure. Or if you specify your Riemann surface, for example, as a hyperelliptic Riemann surface, it's the complex conjugate Riemann surface is given by just the complex conjugate branch points in the complex plane, and then the hyperelliptic covering corresponding to that. So every Riemann surface automatically has its complex conjugate Riemann surface. But of course, as smooth surfaces, they are the same. And then if lambda is not 0, what we can do is the following. We consider lambda connection, so such kind of triple on our Riemann surface sigma. And we map it by a quite simple map, namely 1 over lambda. Basically, we just apply 1 over lambda in some sense, 1 over lambda d, and then 1 over lambda del bar. And we consider this triple on the Riemann surface sigma bar. And we already observed that 1 over lambda d, if lambda is not 0, is somehow a 1,0 part of a connection. But the 1,0 part with respect to sigma is a 0,1 part with respect to sigma bar. So this construction here, sigma goes to sigma bar, maps 1,0 to 0,1 parts, and vice versa. So 0,1 part on sigma is mapped to 1,0 part of sigma bar. So is this somehow clear, or shall I somehow explain that in more detail? So it just interchanges these decompositions because the complex structure J is mapped to minus J. So the decomposition just is interchanged. And from that, we simply can compute that this 1 over lambda d and 1 over lambda del bar is a 1 over lambda connection. 1 over lambda connection on sigma bar. And we all automatically have flatness. So this gives us a well-defined map psi from the Hodge moduli space of sigma. If we restrict that over the pre-image where lambda is not equal to 0, to, and this is a biholomorphic map, of course, to the Hodge moduli space of our complex conjugate Riemann surface, again restricted to C star. And this covers the map lambda to 1 over lambda if we look at these projections to C, just by our definition. So what we then can define is the Delin-Hitchin moduli space, which is just the Hodge moduli space of sigma glued with respect to this map psi with the Hodge moduli space of sigma bar. And by construction, this admits a holomorphic map to CP1. So if we restrict to the Hodge moduli space of sigma, it's just the map pi. But then, the gluing is lambda goes to 1 over lambda. So the point, the Hodge moduli space of sigma bar at lambda 0 would correspond to infinity with respect to this projection. So this is exactly the compactification we are after. And before I explain that in more detail, let me introduce some more notations about that, namely a real structure. So we have a real structure, which in our situation, so more generally, we should use a slightly different real involution. So it's an involution. So C squared should be just the identity, which is complex antilinear. And it's a map from the Delin-Hitchin moduli space to the Delin-Hitchin moduli space. And basically, it's just given by complex conjugation. So it has a very nice and simple definition. So we just map to lambda bar, del bar, bar, d bar, and this we consider on sigma bar. We just take the bars. And I should explain what bar of a operator del bar or of the operator d means. So bar means conjugation by the complex conjugation on our bundle V, which is just the trivial C2 bundle in our situation. So we have the natural complex conjugation, and and we can gauge with that. And if we do that, we can compute that this map C is really a well-defined map. So the operators, because conjugation twice with the complex conjugation is still applying complex conjugation twice gives us a new complex linear operator. We can easily compute that this map really maps to the Delin-Hitchin moduli space, and actually it covers the map lambda goes to 1 over lambda bar. We can just, because the connection lambda bar, the lambda bar connection on sigma bar is corresponding to a 1 over lambda bar connection on sigma. So this maps, which we have just defined here, is covering the if we think of CP1 as the unit 2 sphere, it's the reflection across the unit circle. And yeah, we will make use of that real structure in a second, but let me just give a few side remarks, which might be interesting, at least to Mustafa. So the reason why Delin was introducing that modularized space was as a complex geometric or complex analytic reincarnation of the twistor space of the solutions of the self-relativity equations. So there's an additional involution, let's call it N, which is the map from the from the Delin modularized space to itself, which maps lambda del bar d on the Riemann surface sigma to minus lambda del bar minus d. So this is a well-defined map. And yeah, what one then observes is that N and C commute with each other, so they give a new involution. This involution is covering the antipodal involution of CP1. And then there's a theorem, which was, the details have been carried out by Carlos Simpson, but it's I think it's due to Delin. So the theorem is that the Delin-Hitchin modularized space with this vibration and the involution, the real involution C circ N, is the twistor space of the modularized space of solutions to the self-duality equation of Hitchin. And the twistor space is used to compute the hyperkähler structure on this modularized space of solutions of the self-duality equations. And this can be done in terms of twistor lines, so sections of this bundle MDH over CP1. And these sections are quite similar to our associated family of flat connections, but we have a different kind of reality condition, because for the self-duality equations, they are corresponding to harmonic maps into hyperbolic free space. And this will give us a different reality condition or different Gauss-Codazzi equations than we would get for maps into SU2 or S3. But besides that, the story is quite similar, and one can try to construct all kinds of real sections with respect to tau and construct solutions of the self-duality equations from that. And so this is just a side remark. So let me continue with the theory for minimal surfaces into S3. So the observation, or maybe it's a lemma, maybe it's a theorem, I don't know, let's call it proposition or observation. So if we extend the above section to the Hodge modularized space given by the associated family, we get a section in the Delin-Hitchin modularized space. So what we do is, so we start with the associated family of a minimal surface in S3, and then we can define a section S of lambda, which is given by lambda del bar minus lambda phi star and phi plus lambda del on sigma. So if our family of flat connection is associated to a minimal surface in S3, then this section S of lambda is well defined, extends to lambda is infinity, and is a real holomorphic section. So what does it mean? Holomorphicity is basically clear the Delin-Hitchin modalized space is a complex analytic space. So at the smooth points, we just have a smooth complex manifold, and we have a holomorphic map into that. But it's a section is also clear. It means we project around to the identity. So lambda, we map lambda to S of lambda, a lambda connection, and we project to lambda again. And that this section is real means that if we look at the section at 1 over lambda bar, then this is C of S of lambda. So we have this special reality condition. And right, so maybe, yeah, so this is a nice observation. So it means that from a minimal surface, we get a complex line, so a holomorphic CP1 inside that Delin-Hitchin modalized space, and that it corresponds to a harmonic map or a solution of the Gauss-Codazzi equation, means that we have satisfied this reality condition, and then we should impose certain extra condition that the map is comes from a minimal surface, so there are no periods when we integrate up. This means that we have to go through certain points, and that it's conformal, which also means that we have to hit at lambda 0 specific subspace. So I will specify these conditions in a second, but let me just add one additional remark, which is important here. The set of gauge classes of unitary lambda connections for lambda is in the unit circle is contained in the fixed point set of the involution C. So if we start with a unitary connection and we decompose it into parts and scale the 1, 0 part by a complex number which has length 1, so an element in S1, then we obtain a point in the Delin-Hitchin modalized space. So this point lambda, del bar nabla, and del nabla, and we scale this. And this is in the fixed point set of our complex involution. So of course, the complex involution maps lambda to 1 over lambda bar as before, but lambda is in the unit circle, so 1 over lambda bar is then the same as lambda. And the unitarity of the connection, which is an important condition for us, means that after short computation, it means that this is really a fixed point of our complex involution. So this is an important observation, and from that we can state a very nice existence theorem. So let S be a holomorphic section from CP1 into the Delin-Hitchin modalized space of a Riemann surface, be holomorphic and real, such that the following properties are satisfied. So the first property is S of 0. So we can look what happens at lambda is 0. We have a lambda is 0 connection, so it's a tensor field, and we can take the determinant. And if the determinant is 0, we say that is contained in the nilpotent locus. So this is a condition. S of 0 is in the nilpotent locus. The second condition is that S of lambda 1 and lambda 2 is the trivial gauge class. So the gauge class of a trivial connection or the trivial lambda connection for 2 points, lambda 1, lambda 2, in the unit circle, and both points should not be equal. And the third condition is that that S of lambda, so we have a real section, which means that along the unit circle we are in the fixed point set of a complex involution, of a real involution C, but we need to impose that S of lambda is contained in the unitary gauge classes for lambda in S1. And actually that the section is real can be dropped if we just have a section and we have a third property, then the section, or we have a section over the complex numbers, then the section automatically extends to lambda 0 and is real if we have that this third property holds. And then the statement of the theorem is that then there exists a CMC immersion F from sigma into S3. The mean curvature is determined by these two points, lambda 1 and lambda 2, where my gauge classes are trivial as the gauge between these two. And and such that S is given by the section S, the section I have with the properties, that this section is given by the associated family of F. So just the slide before I explained the proposition that if we have an associated family of flat connections of a minimal surface in S3, and of course this also holds for CMC, then we get a section. So now we have the reverse construction theorem. If we have a section with the properties, then we obtain a minimal surface or a CMC surface determined by this section. So this basically reduces the construction of minimal surfaces in the 3-sphere or CMC surfaces in the 3-sphere or CMC surfaces in Euclidean free space as a complex analytic or complex geometric problem of finding specific curves, compact projective lines inside a complex manifold satisfying certain properties, which is a theorem I like very much. And additionally to the existence statement, we can also make some kind of uniqueness statement. So if for all lambda in the unit circle, the point S of lambda is irreducible or likewise stable. So note that I really exclude the unit circle here with my condition, because there at the unit circle we have the 2 points, the trivial gauge classes, which consists of reducible points. So it's not satisfied that property that S of lambda is irreducible at these 2 points, lambda 1 and lambda 2. But I only need the condition for all lambda which are inside the unit disk. So if this is satisfied, then the minimal surface F is unique. So this is something we can really check in examples, or we could also rephrase that. So if the set of points, their irreducibility is not happening, must be a discrete subset, because otherwise we wouldn't get a CMC immersion, which can be shown. So if irreducible is really necessary to obtain compact Riemann surfaces of higher genus. So maybe I should go back to the previous slide and add a condition here. Sigma should be compact. And if one doesn't have compact Riemann surfaces, one would need to impose certain boundary conditions such that the theorem can work. Okay, so if we really want to make the CMC surfaces of genus greater or equal to 2, then we need irreducibility for generic lambda, for generic spectral parameters, and then the set of points where reducibility fails is a discrete or a finite subset of CP1, and it can be shown that for each point where this doesn't hold irreducibility, there is a certain kind of transformation of the CMC surface or minimal surface, which is known in more classical language. It's a so-called dressing transformation. So if you think about your CMC surface as some kind of alignment of certain bubbles, so basically chain of spheres connected by certain necks, these kind of transformations somehow push the bubbles around. So maybe you have seen videos or pictures of that phenomena for tori. This is given by the linear flow described by Hitchin in his paper. We haven't observed such kind of CMC or minimal surfaces for higher genus yet. So in all the examples we did, we automatically have that this condition here is satisfied and we obtain a unique minimal or CMC surface. Okay, so that's somehow the reconstruction theorem. And if you have some question now about the general meaning of the theorem, maybe that's a good point. Otherwise, I would start to indicate how to prove that theorem, how to obtain from these complex geometric data, from this holomorphic curve or holomorphic projective line inside this complex manifold, minimal surface or CMC surface. So if there are no questions, so I will start with the sketch of a proof. And so there are 3 steps we have to do. So the first step is we lift our section. So S is a map from CP1 into this basically Delin-Hitchin moduli space. So if we restrict to C, so then it's just a map into the Hodge moduli space. And this Hodge moduli space is the space of all lambda connections modulo the gauge group. So it's a map into a quotient. So what I mean with a lift is we search for a lift into the space of lambda connections. And this is motivated by the so-called DPW theory somehow. So I will explain a little bit about that in my last talk. So you can try to find specific coordinate systems on the space of lambda connections and write down these sections in terms of these coordinates on the moduli space of lambda connections. But we can also do this lifting without the DPW setup and just find a certain kind of lifts. I will explain how this works in a second. But if we are able to find a lift, so given by a family of flat connections, namely a family nabla tilde lambda, which starts with a with a 1-0 form. Then we add a connection, and then we add higher order terms. But now we are allowed here to add infinitely many additional terms. So that's a huge difference now. We start with a lift which has not the form of the associated family, but we just look for some kind of lift which starts at the lambda inverse term and then has maybe infinitely many Fourier modes in terms of lambda. But I shall explain how we can find these lifts for every section in a second. So right, then the second step would be to gauge this lift nabla lambda into our form, into the associated family of flat connections form. So this means that we want to find gauge transformation which somehow removes all the parts starting at lambda squared, and to make this connection nabla tilde unitary and psi1 to be minus phi star. So this would be the second step, and if we can manage that, then we have an associated family, because we just have the properties where we can take the gauge transformation between the connections at these two special points where we hit the trivial gauge class, and this gives us automatically our CMC surface. And then the third step would be show uniqueness or study uniqueness. So these are the three steps we have to achieve here, and let's try to do that. So right, we should start with the first point. So we should try to construct some kind of lift, and locally on C. This is basically by construction of this moduli space of flat connections or of flat lambda connections. So it's always it's always true that you locally can find lifts. So locally on maybe simply connected subsets, U alpha subset C, there exists lifts. Of the section. So families, nabla alpha of lambda, which is a flat connection, and of course, if U alpha contains lambda 0, it has exactly the kind of asymptotic behavior we want to have. And now we can construct a cocycle, and basically we use irreducibility, at least for generic lambdas, to obtain the cocycle condition. So what we get is there exists maps G alpha beta from our intersection of these two subsets in the complex domain in the spectral plane into our complex gauge group, satisfying the cocycle condition and the property that nabla beta lambda is exactly nabla alpha lambda gauged by this gauge transformation G alpha beta. So this this basically comes from the fact that we have two different lifts locally on the intersection, and the lifts, because the connections are at least generically irreducible, they differ by basically unique gauge transformations. And if we apply that twice or several times, we automatically get the Cocycle condition. So we get a Cocycle with values in some kind of infinite dimensional Lie group, this gauge group, but still there are some useful theorems about that, and particularly there's a certain generalized Grauert theorem about vanishing of certain cohomology classes. So in our situation, we can just apply this generalized Grauert theorem, which says that there are maps H alpha from our set U alpha into this gauge group, such that G alpha beta is H alpha times H beta inverse. So because we have a simply connected domain C, and because we have a Cocycle with values in some complicated group, of course, but still we get that the Cocycle is trivial. So it's given by H alpha times H beta inverse for specific maps. And then what we get is that nabla hat lambda, which is I take nabla alpha, the local lifts lambda, and I gauge them by H alpha of lambda, of course. This is well-defined, is a well-defined lift. As specified before. So we locally get these lifts into the space of lambda connections or into the space of flat connections, and we can put them into a nice form which starts at lambda inverse and then has infinitely many terms approaching lambda's infinity. But at least we get this lift. And now then there's the second step, which is basically a counterpart of some existence part of the DPW method. So I originally learned it from DPW or Dorfmeister, Pellet, and Wu. Similar techniques have been applied in integrable system methods before. So, and it uses similar. This is similar to DPW, and it uses so-called loop group factorizations. So what are loop groups? And I do not go into the analytic problems here. So if you want to learn about loop groups, you should definitely consult the book by Presley and Siegel. But of course, there are also short, simpler accounts. For example, you find all the necessary material in DPW paper, in the original one. So we define the loop group or the SL2C loop group as the map of as the space of real analytic maps from G from the unit circle into the group SL2C. Okay, so this gets or is automatically a group by pointwise multiplication, and if we have two real analytic maps on the unit circle and we multiply them pointwise, we get a new real analytic map. So this has a well-defined nice group structure, and there are specific subgroups we shall make use of. Namely, there's the positive subgroup, and it's given by those loops which satisfy the property that G extends to lambda is 0, and there's the so-called unitary subgroup. These are those real analytic maps into SL to C, which actually map into SU2. So G of lambda is in SU2 for all lambda. And then there's some kind of subgroup of the denoted by lambda plus B, which is a subgroup of a positive loop group given by the property that G of 0 is an upper triangular matrix with real entries. So R stands for a real number or a positive real number. And we have these loop groups, and then there's a counterpart of these finite dimensional factorization theorems for loop groups with respect to compact subgroups, like for example, if you have a group SL to C, you can split into by standard observations into the unitary group times the group of matrices which exactly look like this here, the G of 0. And we get a counterpart of that for these infinite dimensional groups. Namely, what we have is the so-called Iwasawa decomposition. So this Iwasawa decomposition says we have a real analytic diffeomorphism of the loop group into the positive part of the loop group with this additional property times, so pointwise multiplication or multiplication in the loop group times the unitary loop group. So this is the infinite dimensional Iwasawa decomposition. So there are several ways of proving that. Nice and somehow almost finite dimensional proof is given a paper by Donaldson, but also you could use the Birkhoff factorization or the classification of holomorphic vector bundles over CP1, and then the corresponding Birkhoff factorization of these bundles or Grothendieck decomposition of these bundles, and study this decomposition, and you can prove from that you really get this kind of diffeomorphism of the splitting of a general loop into a positive loop, so a loop which extends holomorphically times some unitary guy. Okay, and we need to use that Iwasawa decomposition, and let me try to go into details here how we do that. So we start. We have our lift now. So proof of 2. So start with the lift. We just take any nice lift, tilde nabla lambda, which is lambda inverse 0,1 form, plus some connection and so on, infinitely many other terms. But the reality condition our section satisfies can be rephrased. There are different ways to rephrase that, but maybe the best way of doing that is that, or at least for this moment here, is that for every lambda on the unit circle, there exists Hermitian metric I denote by as such, and so this comes from the fact that all the connections are contained in the unitary gauge classes, but we take some kind of arbitrary lift, or I mean not totally arbitrary of course, but holomorphic lift, but we somehow lift, and there's no guarantee that the connections are still unitary if we apply a complex gauge transformation. But if we apply a complex gauge transformation, it means that our Hermitian metric can also be gauged such that it's again unitary for the gauge connection. So it means, at least this is the idea. So it means that we should think of these Hermitian metric depending on the spectral parameter lambda as gauge transformations of or pullbacks of the standard Hermitian metric. So we can prove the following thing: there exists a unique, basically, map H or H lambda, maybe H in the loop group, in the loop group, or better say, there exists a map H from S1 times our Riemann surface into SL2C. And we can interpret this as a map from the Riemann surface into the loop group, and such that our Hermitian metric, depending on our spectral parameter lambda, is just the standard Hermitian metric pulled back by this H lambda. Okay, so this follows basically from unitarity, and for example, we would need to prove real analyticity in terms of the parameter lambda, but this can really be done nicely using, basically in our situation, at least for higher genus surfaces, using irreducibility. So this is not a problem here really, and what we can do then is we apply this gauge transformation after factorization. So what we do is we look at this loop H lambda, depending of course also on the point on the Riemann surface, and we take the inverse loop and we decompose it into the positive part. So this is in lambda plus, and to make it unit, we specify the condition at lambda is 0 times the unitary part. And if we do that, and if we apply the unitary transformation to the Hermitian metric, it just means it doesn't change the Hermitian metric. So if we do that, we can compute that the following, namely nabla lambda, which is our lift gauged by this positive part by B of lambda, is unitary, not anymore for this Hermitian structure, but is unitary for the standard Hermitian metric for all lambda on S1. So this is a crucial but simple observation here, because of course the unitary loops act trivially on the standard Hermitian metric. And the second important observation is that because B of B is positive, it just conjugates the lambda inverse part. So our new family of flat connections, the gauge family of flat connection, so is actually of the form nabla lambda is lambda inverse phi plus nabla, and then we only have a lambda part, And because of unitarity with respect to the constant Hermitian metric, we see that it's exactly of this form. And then, as a consequence, is the associated family of a CMC surface. So once we have this form here, and we know that these connections are trivial for at 2 points, we can again apply the gauge transformation, which gives us map into SU2, and we can compute that it's a CMC surface, or maybe even a minimal surface if λ1 and λ2 are plus minus 1. And yeah, I think we have a few more minutes, but I do not want to go too much into details about this third point. So the idea is to study possible different lifts of that form, and to prove that they only exist if there exist reducible connections, lambda connections. And whenever there exists such a reducible lambda connections, we can apply some kind of transformation. But if there are no reducible connections at all, we have a unique somehow lift. And this means we have a unique minimal or CMC surface. So third point can be done by looking at possible gauge transformations depending on the spectral parameter lambda. And then one uses an old trick I learned from Hitche, namely one at lambda 0, one has not a gauge transformation of a connection, but only of a holomorphic structure and a Higgs field. But this can be done nicely, and you can find it in my paper, Spectral Curve Approach to Lawson symmetric CMC surfaces, how this step can be carried out in detail. So yeah, let me just end with some for today with some remarks here to indicate that this is not just abstract nonsense, but one really can learn something from this approach and determine things explicitly. So one of the nice things is that there's a nice way to compute the area of the surface in terms of these holomorphic sections. So basically there's a functional I denote by E for energy, which maps the space of holomorphic sections, or maybe more particularly the germs of holomorphic sections of from CP1 to the Delin-Hitchen moduli space into the complex numbers. And yeah, this is basically the space of holomorphic sections can be seen as a complex analytic space by Kodaira-Spencer deformation theory again. And this energy is a holomorphic. It's a holomorphic map on the space. But if we apply it to a section which satisfy our properties, our three properties I have stated in the theorem, namely here. So we have we have that we are in the nilpotent locus. We have that it's unitary, and we have that is corresponding to a trivial gauge classes. Then it's, we can compute that it's the area with energy functional. It's just the area is up to a scaling, maybe is the area of the corresponding minimal surface. And the functional can be written down quite nicely. So if we take any lift as before, nabla tilde lambda, which starts with some lambda inverse term, tilde phi plus nabla plus lambda psi. What we do is basically E of this section given by this lift is some scaling, maybe 2 minus 2i. And then we integrate this lambda inverse part compared to the lambda part. So what we do is we take the trace of this tilde phi wedge psi. And of course, psi could be a 1-0 form or a 0-1 form, but or a mixed form. But this is what we get out of the energy. So basically it tells us if we have non-constant maps, psi automatically needs to be have to have a 1-0 part. So we can compute quite nicely the energy out of these data. And in fact, this is a nice generalization of the energy formula of Hitchin in his original harmonic 2 tori paper, where he used the data of the spectral data. So basically, we have a spectral curve somehow specifying what I now call a section of the Delin moduli space. And then we have these differentials. And this energy formula written down here is an analog of an energy formula of Hitchin in terms of somehow the expansion of the meromorphic differentials on the spectral curve. So it's a quite nice and actually also a very useful formula. So in the last talk, I will explain how we can use this theorem to really study surfaces and find out certain properties of the surfaces. In particular, we can find out certain information about areas of Lawson surfaces, and we exactly use this formula here to do these computations. So maybe a last remark about this is that the energy functional as defined was somehow motivated by still another work of Hitchin on the self-delete equation, on the moduli space of self-delete equations. So this is a nice hyperkähler manifold, as said before. It has a circle action, and then on the space of on the twistor space, there's a natural holomorphic line bundle in many situations, and this line bundle has a meromorphic connection, and somehow the energy can be seen as the residue of this meromorphic connection. And this somehow seems to play an important role in some of the works done by physicists in the recent years about construction of hyperkähler metrics in terms of integral equations, for example, by Gayot and Moor-Neitzke. So it connects nicely to some recent work by theoretical physicists. But maybe that's a good point to stop for today. And maybe you have some questions.
Any question? All right, thank you very much, Sebastian, for the nice talk.
Welcome.